Hello, folks. Let me adjust this just a little bit. Hi, I am Roger W9, and I got some more commentary. This one is going to probably be a little bit controversial because what I talk about is some of the personnel decisions made by the Boeing company back in the 1990s that I believe has led to the problems with the 737 MAX and the adaptation of the CFM LEAP engine to the 737 airframe. And it's my opinion that the 737 airplane frame was never designed to carry such a thing that has such a large outside diameter. But based on what we know about the CFM LEAP engine and what a big improvement in fuel efficiency that it represents, it would have been well worth it to design an entire new airframe around this engine. We're talking about a 15 to 16% better production of pound seconds of thrust impulse for each pound of fuel burned, or each gallon of fuel, or each kilogram, each liter of fuel. However you measure the fuel, for each unit of fuel burned, we're getting 15% more pound seconds of thrust. And once you have this engine available, if Airbus is selling an airplane with this engine on it, Boeing has to offer it or it simply cannot compete for the airlines. Imagine, if you will, somebody invented a steam cycle that generates electricity that was getting 15% more kilowatt hours out of every ton of coal burned, or every 1,000 cubic feet of gas burned, or every pound of U-235 fissioned. Well, such an improved steam cycle, pretty much every new power plant would have to incorporate it, provided that they can build it for only 20 or 30% more than traditional steam cycles. But even if it's like 50%, it might be well worth it just from the fuel savings over the lifetime of the power plant to incorporate such a new steam cycle. Now, such a steam cycle hasn't been invented yet, so we're stuck with the 40% efficiency of existing coal and gas-fired steam cycles. We're not going to get a 46% fuel efficiency for the time being unless somebody invents something entirely new. But that's neither here nor there. But CFM managed to do that, mainly by increasing the bypass ratio from about 5 or 6 to 1 with the CFM 56 engines up to 11 to 1 for the CFM LEAP engines. Now, I can go in to explain to you this, but I think I'll leave that physics out of the equation because now I'm going to talk about how Boeing shot itself in the foot back in the 1990s with the this bird, the 777. See how pretty it is? A beautiful bird. It's just taking off. This one is an Air France bird taking off, and you see at a high angle of attack, and it's climbing. It just took off from the runway. But here's the thing. This is a diagram of the outsourcing, as you see. In fact, I'm going to lay this down here, and I'm going to use this camera to show you how it is. Okay, now you see it. I labeled it 707 outsourcing, and then I labeled the bird. You see KHI and MHI on the sections fore and aft of the center part where the wings are, and I labeled FHI. KHI stands for Kawasaki Heavy Industries. MHI stands for Mitsubishi Heavy Industries. And I got the shadow over the image. But FHI, the center section where the wings join the plane, were made by Fuji Heavy Industries. Now we got things like what they call the elevators or the horizontal stabilizers were made by Hawker Industries, famous for making the Hawker Hurricanes and the Hawker Typhoons during World War II. But they're now a descendant company of that, and they merged with some other companies, and amongst other things, they built the ailerons. So this had some serious consequences. As you can see, very little of the aircraft is actually made by Boeing. It's assembled by Boeing at the Everett plant where the 777s are assembled. But only this part, maybe the cockpit, most of the wings, but a lot of the parts on the wings are outsourced. And some of the tail portion, not including most of the tail feathers, although the vertical fin, except the rudder, is probably made by the company itself in places like Auburn, where they machine the parts, they machine the wing spars. But that's pretty much a major outsourcing. Birds prior to the 777, you didn't have the entire body section outsourced to Japan. They were built by Boeing, mostly. You know, a lot of the parts might have gone somewhere else, but the major structural parts were machined in Auburn and other such places, then used to assemble the birds. So this is one of the things that happened during the 1990s with the 777. Now, I'm going to go back here and tell you that the consequences was that I was an engineer assigned to the 777 project, but the work that I was doing struck me as very boring and chicken droppings work, or chicken shit work, essentially. But chicken shit that it was, it gave me a chance to look at the design models of pretty much every system on the 777 during the several years I was there in working in Everett. Now, why do I think it's chicken shit? Well, I was taught how to calculate force vectors. I was taught how to calculate stresses. I am familiar with such equations as stress is equal to mc divided by I. I'm a pretty smart guy. Yet in this job assignment, they made me feel like Frito Corleone. You know, I'm a smart guy, and yet I'm doing this crap. Doing the work that pay code 2 type folks should be doing. And here I am, a pay code 4 engineer. So, you know, I'm pretty frustrated. And I didn't like that. But why, then, were so many experienced engineers doing similarly chicken shit work? We're doing the design work that we can sink our teeth into. And part of it is because, well, the body section, which is most of the airplane, was outsourced to Japanese companies and to British companies, European companies. Let me show you another drawing I made from the same print. Let's see. Let me give you a look at this. I'll pop this so I can see it. Again, you see the force vectors. Here you look at the force vectors of the airplane on the ground. You got the center of mass is a little forward of the wings. You got underneath the wing box the main landing gear, and you got a reaction at the main landing gear, and you got a reaction at the nose gear, which is a little smaller. This is why the main landing gear has got lots and lots of tires, a big heavy thing, and the nose gear has 2 tires and it's a little itty bitty thing. But the center of mass is a little bit forward, and the plane sits on the ground at a very level angle of attack. Now, we look over here, and you see I drew in the major structural elements in this plan view of the 777 bird. This is typical of pretty much every jet age airline, or large jet airplane since the 1950s, since the 707 project, the Dash 80. You have the center big structural part, the wing box, right there. You have the wing spars attached to the wing box, and they go out this way. And the longerons run up and down the bodies, at least as far as the rear pressure bulkhead and the main structural elements of which the tail feathers are attached. So, those are the parts. Well, here's the thing. When we outsource the body sections, including the center wing section, to these Japanese companies, we outsource much of the engineering design work of the wing box and the longerons. I repeat, Boeing outsourced much of the design work of the wing box and the longerons to these 3 Japanese companies. with Fuji Heavy Industries doing the wing box. You're going like, what? But that's what they did. And I know this because I worked there at the time. And I saw all these drawings, computer type drawings, models of the various parts of the birds, including the wing box sections. And they were brought in from Japan. And then we had to adopt that in the I believe, well, it's not what they call the Dassault computer aided design. I forget the name of it right now, and I'll remember it one of these days. But it doesn't matter. It's a computer pre-assembly, digital pre-assembly type of things. And we got some improvements. The parts fit together better in the 777. But most of the engineering design work that a guy like me could sink my teeth into, calculate force vectors and calculate stresses and calculate and decide how big the fillet should be to avoid metal fatigue problems in the aluminum parts, that was outsourced. And it was Japanese engineers who did that work. There were some American engineers in Boeing on the senior level, W-18 and W-20 PACO type levels. They probably mentored the Japanese engineers in getting this through and improving the final designs so that that we have a safe bird to fly. But one of the things that happened at this time, because of this outsourcing of the engineering work, was that a large number of 40-something and 50-something structural design engineers, aircraft engineers who were at that age, had lots of valuable experience that they could use to mentor guys that were at my age and younger, 20s and 30-somethings, to become the next generation of that core group of experienced aircraft structural designers, were bought out with early retirements. And then we had layoff exercises throughout the whole time. We're ramping up to design and ramping up to start assembling the 777. So what happened is we had a successful company taken over by Milo Minder binders and bean counters. I guess American labor just got too expensive for them. Prior to the 1990s, every bird that Boeing built, the structural design was in-house, done by Boeing engineers, Americans basically employed in the state of Washington. This happened with the Model 243, this B-17 and B-29 birds, the B-47 jet powered bomber, B-52s, we did that, and then on to the 707 series of aircraft, 707, 27, 37, 47, 57, 67. And what happened was that with each new bird that Boeing built, Boeing designed, the core group of aircraft structural designers who had experience with wing boxes and longerons and the hoops, basically the ribs they call frames for what they call the body and what some people call fuselage, and the tail fins. This core group would mentor a new generation of 20-something and 30-something engineers to become the next generation core group of experienced designers in the 40s and 50s age range, in their 40s and 50s and on into the 60s. So that's how Boeing did. And when I hired into Boeing at 1984, one of the most attractive things about getting a Boeing job in the 1980s was this core group of experienced aircraft structural designers, where if you can just get in where you're going to be mentored in, you can become one of them, and then you can buy a nice big house in Marine Hills and Federal Way like my father did. And he designed like the control systems, the control cables that ran through the floorboards. And of course, and when I told him that with the 777, we're doing away with most of those cables and we're using fly-by-wire with electronics, he kind of groaned and says, well, I hope that works out. Essentially, we were computerizing and electronicizing the flight of the aircraft, the controls of the aircraft. But, most of the aircraft, the 777s, have turned out fairly well. In spite of all this, outsourcing and expecting Japanese engineers to do the job that American engineers used to do. Uh, and all the supply chains that have been outsourced to all over the place, including these big heavy industry companies in Japan. But, they say, we had that Malaysian bird that dropped into the Indian Ocean. Nobody knows why or how that happened, although some people think it was pilots committing suicide by taking their passengers and flight crews with them, which, you know, I don't understand that myself, but then I don't understand why a guy who worked so hard to become an airline pilot would then throw it all away. Who knows? A lot of things don't make sense. But how this can affect, like, the 737 MAX engine is that the 737 MAX is built with the CFM LEAP engine, which has this big outside diameter, like over 100 inches. I mean, by contrast, the engines that you see on the 777 have an 110-inch diameter that they're built on there. They're almost as big around as the entire body sections of the 737. 737 is 10 feet and 8 inches, or 128 inches across, and the cowling you see around these engines that are on the 777 about 110 inches. So it's only 18 inches less in diameter than the entire fuselage or the body of the 737s and 757 type planes. But that's the thing, and then they wanted to put this big engine up on a 737 airframe. Why didn't they just design an airframe around this engine so we have a safe bird to fly? Because Boeing no longer had a core group of aircraft structural designers. A core group of 50-somethings and 60-somethings. Now, they got 50-something and 60-something engineers, 40-something engineers who are experienced, but they're experienced in doing, I don't know, the kind of chicken shit work that I was doing.